Okay, let's review Thermodynamics 1. So this one is specific heat. So if you want to determine the specific heat of your system, we can use this equation for internal energy. So if you want to determine the change in specific internal energy U, we can use CV times the difference in temperature. If you want to determine the change of enthalpy, then we can use CP. Okay, so these are how we can use specific heat to determine the change in specific internal energy or specific enthalpy. So let's solve one problem together. So we have a spring-loaded piston cylinder device contains 1 kilogram of CO2. The system is going receives heat from 100 kilopascal, 25 degrees Celsius to 1000 kilopascal and 300 degrees Celsius. We want to determine the amount of heat transfer and energy transfer by work. Okay, so let's do that. So we have this spring-loaded piston cylinder device, and there's a CO2 inside. Initially, T1 is 100 kilopascal, T1 is 25 degrees Celsius, and this one is 1 kilogram. And we have a heating process that means we have Q in. Because of this Q in, the final pressure is 1000 kilopascal, and the final temperature is 300 degrees Celsius. So if you want to analyze this CO2, we need to write the energy balance equation. The energy balance equation is for a closed system, it's going to be Q in plus W in minus Q out minus W out, which is mass times the change in its internal energy, U2 minus U1 plus moving boundary work. So from this, we have a heat transfer Q in. That means the surroundings of this piston cylinder device is at a higher temperature than the system. That's why there's a heat transfer from outside to the system. So we have Q in. That means there is no heat loss from the system because the system is at higher temperature than the surroundings. Due to the second law of thermodynamics, heat only transfers from a higher temperature point to a lower temperature point. And there is no information about energy transfer by work other than this spring work. So spring work is this moving boundary work because of the spring, this piston moves up and down. That will change the volume. Therefore, this is the moving boundary work. There's no other energy transfer by work, so you can neglect W in or W out. So we have Q in is mass times U2 minus U1 plus moving boundary work. This one is the unknown. We know the mass 1 kilogram, and U2 minus U1 can be determined by this specific heat, U2 minus U1. In other words, the difference in specific internal energy, U2 minus U1, is CV times the difference in temperature, T2 minus T1. So this is the equation we are going to use. So here we have mass times CV T2 minus T1. And we already know the initial temperature, 25 degrees Celsius, and the final temperature, 300 degrees Celsius. So we have this one, we have the mass, we just need to determine the specific heat. And how can we determine the specific heat? From this table A20, ideal gas specific heats of some common gases. Okay, so there's a CV. So there are many specific heat values. So which one are we going to use? Just randomly select one of them? No, we have to, use the average temperature between 25 and 300. So what is the average temperature? 325 divided by 2, 162.5. So the average temperature, the average is 162.5 degrees Celsius. However, if you look at the unit of the temperature on this table, it is Kelvin. So you have to add 273. So what do we get? 435.5 Kelvin. So we have to use the specific heat, evaluate it at this average temperature. So it's going to be between 400 and 450 Kelvin. So CV value we are looking for is between these two numbers. So how can we determine the exact CP value? We can use linear interpolation. How can we use linear interpolation? We have 400 degrees Celsius, 450. So this is the linear interpolation equation. The left-hand side is temperature T. The right-hand side is CV. We have 400 and 450. We have 400 and 450. The CV value at 400 is 0.75. At 400, 0.75. The CV value at 450 is 0.79. 0.79. Then, what is the temperature that we want to evaluate specific heat? 435. So I'm going to write 435.5 here. Then the unknown CV value is going to be at the same location, top left of this left-hand side, top left of this right-hand side. Then we have 450 here, and we have 0.79 here. So we can determine the specific heat, CV, at this temperature. Okay? So if you do, linear interpolation calculator. I don't have a calculator, so I have to use this one. So 400, 0.75 for 33, 35.5 and 45, 0.79, and I get 0.7784. So going back to this equation, this CV is 0.7784 kilojoule per kilogram Kelvin. What about the mass? 1 kilogram. What about T2? 300. What about T1? 25. Then you may have a question. There's a Kelvin. Can we use degrees Celsius? Yes, you can, because we are multiplying this CV by the difference in temperature, not just temperature. So 300 minus 25 is the same as 300 plus 273 minus 25 plus 273. So the difference in degree Celsius is the same as the difference in Kelvin. So you can use 300 and 25. You don't have to convert them to Kelvin, okay? Then we have everything here. The only unknowns are WV, WB, and Qin. So we don't know how to determine this Qin other than this energy balance equation. So we have to determine this WB to complete that equation. How can we determine moving boundary work when you have spring-loaded piston cylinder device? You may remember that the last time we did a free body diagram to determine when we use PV diagram, we have a straight line. If you don't remember, you can review the lecture video that I uploaded on Blackboard. You know that if you go to Blackboard, you can find the lecture video, right? Then let's find the initial state. So we have 100 kilopascal, 100 kilopascal. We have the final pressure, 1000 kilopascal, 1000 kilopascal. What about volume? Oh, we don't know the volume of the system. So how do we determine the volume of this carbon dioxide? By using specific heat, we can only determine specific internal energy or specific enthalpy by specific heats. Instead, we can use ideal gas equation. So the ideal gas equation is PV is mRT. We can use this PV mRT at the initial state. P1 V1 is mRT1. Why don't I say M1R1? Because it's a closed system, mass is constant. So there is no M1 or M2, just M, right? What is this R? It's a gas constant. So there's no change in R between the initial state and the final state. So there's no R1, R2. So what is M? 1 kilogram. What is R? Do you remember how to determine R? It is universal gas constant R bar divided by molecular weight. What is the universal gas constant R bar? Always 8.714 kilojoule per kilomole Kelvin. What about this molecular weight? The molecular weight of carbon dioxide can be found from table A1. Table A1. Where is carbon dioxide? Right here. The molecular weight, M, capital M, of carbon dioxide is 44.01. By the way, this capital M is not a mass. Mass is a lowercase m. The capital M is molecular weight. The mass of a substance whose molecular number is, whose number of molecules are 6.022 times 10 to 23. 10 to 26 because we have a kilomole. So, that's oxygen. Carbon dioxide, 44.01. Back here. 44.01 kilogram per kilomole. And what about this temperature T? The initial temperature 25. So I'm going to write 25 here, and pressure is 100 kilopascal. So I'm going to say 100 kilopascal. So if you solve this ideal gas equation, you get V1. Is that right? No. What is wrong here? This should be in Kelvin, right? Not 25. It's going to be 298 Kelvin. Then you determine V1. If you do, V1 is 0.5629. 0.5629 cubic meters. We can use the same equation for the final state. P2V2 is nRT2. So in this case, what is the final pressure? 1000 kilopascal. Mass 1 kilogram. There is gas constant and temperature is 300. So write 300, not anymore, 573 Kelvin. So from this, you can determine V2. V2 is 0.1082 cubic meters. So there is 0.1082 cubic meters. There is 0.5629 cubic meters. So we have 100 and this one. So here is the initial state. Here we have the final state. And we know when you have a piston cylinder device, we have this. This one is a straight line. So if you determine the area here, this area is going to be moving boundary work. By the way, do you know how to determine the moving the area of this shape? If you have this kind of geometry, the way to calculate is the way to calculate the area is simple. This one is A, this one is B, and this one is C. The area can be determined by A plus B divided by 2 times C. That is the area. So technically, we are calculating the entire area. So assuming that this one is B, this one is A. So how do we calculate the area? It's going to be A plus B times C. But it is only half of them, so we divide by 2. Okay. So if you determine the area of this PV diagram, you get 250.1 kilojoule then we go back to this energy balance equation. There is WB, so we write this number there, 250.1 kilojoule. Then we have everything but Q in. Can you determine Q in this way, or did I make any mistake in the process? When I say like that, it sounds like I made a mistake, right? So I made a mistake here. So what is it? It's not a calculation mistake. So tell me what mistake I made in the process. No, it's okay. The entire area is the moving boundary work. Okay? Yes, it's a compression process. Initially 0.5 something, and finally only 0.1. So is it an expansion process or a compression process? It's a compression process. The moving boundary work, WB, is a positive value when it is an expansion process. It is a negative value when it is a compression process. However, when you calculate the area, it doesn't give you the whether it is positive or negative. It's always a positive value. So you need to determine the sign of this one based on whether it is expansion or compression. So it's a compression process. So moving boundary work should be minus 250.1. Then you can determine Q in. That's how you solve this problem. Any question? No. You have a calculator. So there's a final answer from the book, but I don't trust it. Because the book assumed that the CB, and they use the CB value at 25 degrees Celsius, just for convenience. Is that right? No. You have to use a specific value at the average temperature. So the answer from the book, if you have a solution or something, it is incorrect. So the specific heat value used in the solution of the book from the publisher is 0.657. Where is 0.657 at 300 Kelvin? So they evaluated the specific heat at 300 Kelvin. Does it make sense? No. But it's just for convenience for them. They didn't want to go through the linear interpolation. You have to use a linear interpolation to get an accurate value. Okay, so that's everything about this one. We have one more example. An ideal gas contained in a piston cylinder device undergoes an isothermal compression process. Which begins with an initial pressure and volume. So we have the initial volume, initial pressure, and during this process, there is a heat transfer of 60 kilojoule from the ideal gas to the surroundings. So that's a Q out. Determine the volume and pressure at the end of the process. Okay, we can do that. So we have a piston cylinder device. It contains an ideal gas. We have no idea what it is. But if it is a real gas, like oxygen, carbon dioxide, when they behave like an ideal gas, what is the condition? If you have an air, can we say air behaves like an ideal gas? No, we cannot say that. It's only a certain condition. What is the condition? The definition of ideal gas is a gas whose molecules can move randomly, freely. So when that happens, when the density value is low, when gas density goes down, when temperature is high or pressure is low, then density value goes down. So when you say ideal gas, if you have a real gas like oxygen, carbon dioxide, nitrogen, etc., if you want to use ideal gas equation of state, you need to make sure that it is not under high pressure. That means it is not at low temperature or high pressure. Okay? So this one is undergoing an isothermal compression process. That means temperature T remains constant. So P1 is 100 kilopascal. V1 is 0.6 cubic meters. And T1, I don't know, but it is the same as T2. What about the mass? I don't know. And there is heat transfer from this ideal gas to the surroundings, which means Q out. And we have no idea about the final process of state, but we want to determine P2 and V2. So let's do that. So to analyze this ideal gas thermodynamically, what is the number one thing that we need to do? Write down the energy balance equation. What is the energy balance equation? Q in plus W in minus Q out minus W out is mass times U2 minus U1 plus moving boundary work. And there is Q out, this one. That means the system is at higher temperature than its surroundings, so there is no Q in, not possible. And this U2 minus U1 can be determined by CV T2 minus T1, but we know it is an isothermal process. T1 is the same as T2, so this one goes away. There's no information about energy transfer by work other than moving boundary work, so you can neglect these two. So the only thing is minus Q out is moving boundary work. Then how do we determine the moving boundary work of an isothermal process? We studied it a long time ago, when we were in EGR456. So let me give you a brief summary of how do we determine moving boundary work. Besides the PV graph that we used in the previous problem. So if you have a constant volume process, moving boundary work is 0. Of course, there's no volumetric change. There's no moving boundary. When you have constant pressure process, moving boundary work is pressure times V2 minus V1. When you have constant temperature process, moving boundary work is PV natural log V2 over V1. This PV can be either P1 V1 or P2 V2 because P1 V1 is the same as P2 V2 when you have constant temperature process. And finally, polytropic process. Then moving boundary work is P2 V2 minus P1 V1 over 1 minus N. And lastly, we can use PV diagram. And we use this PV diagram for the previous spring-loaded piston cylinder device. And if this one is an isothermal process, moving boundary work is P1 V1 natural log V2 over V1. So let's do that. We can use this equation. WB is P1 V1 natural log V2 over V1. And what is the amount of heat transfer? 60 kilojoule. So Q out is 60 kilojoule. What is P1? 100 kilopascal. V1 is 0.6 cubic meters. V1 is 0.6 cubic meters. So we have only one unknown in this equation, which is V2. So can you determine V2? Yes, you can, right? We have everything but V2. So if you do, V2 is 0.221, 0.221 cubic meters. So we have one equation. We know Q out 60 kilojoule. WB is P1 V1 natural log of V2 over V1. We know P1 V1. So the only unknown in this energy balance equation is V2. Where is mass? Oh, this one? Yeah. T2 is the same as T1. So T2 minus T1 is 0. So this whole thing goes away. Mm-hmm. Then finally, we also want to determine P2. How can we determine P2? P1 V1 is the same as P2 V2. P1 V1 is the same as P2 V2. When you have constant temperature process and P1 is 100, V1 is 0.6, V2 is 0.221 cubic meters. Now, can you determine P2? Yes, we can. So if you do 272 kilopascal. Then you may have a question. Why P1 V1 is the same as P2 V2? It's simple. Think about the ideal gas equation. When you have an ideal gas equation, PV is nRT. Let's assume that you have a constant temperature process. When you have a closed system, what determines a closed system? When everything is closed? No. What it makes a closed system? Mass is constant. So this M is constant. What is R? Gas constant. Is it a constant or variable? Very silly question. The name is constant, right? So mass is constant, R is constant. What about this T? Our assumption is that temperature T is constant. So whenever you have a constant temperature process, the right-hand side of this equation is constant. So no matter what temperatures, what volumes or pressures you find from this system, P times V should be always the same number. That means P1 V1 is the same as P2 V2 is the same as P3 V3 is the same as P1000 V1000, etc. Okay? Whenever you have a constant temperature process. So we can use P1 V1 is P2 V2. We have everything but P2. Can you determine P2? Yes, yes. Yeah. That's why you cannot believe the solution from the book. I mean, I got this number from the solution. So this number may be incorrect. So don't trust the solution, okay? Solution manual. But procedure is the same. So if you didn't make any mistake, you should be at the right, the V2. Any other question? So that means when you do your homework assignments, do not trust your solution manuals. Okay, I highly recommend you do your homework alone, rather than the reading through your solution manual. Okay, don't trust their values. There are lots of mistakes. So any other question about this this problem? No. Okay. So I think that's about chapter 3. We have a few more. Oh, let's look at this problem. Mhm. We have a 1000 watt iron whose base plate is made of 0.5 centimeter thick aluminum alloy. We know the density and specific heat. The base plate has a surface area, and we know the surface area and also the thickness, 0.5 centimeters. And the iron is in thermal equilibrium with the ambient air at 22 degrees Celsius. That means that the initial temperature of the system is at 22 degrees Celsius. Assuming 90% of the heat generated in the resistance wire is transferred to the plate, determine the minimum time needed for the plate temperature to reach 200 degrees Celsius. So the first thing you need to do is that, what is our system? Air, resistance wire, or the base plate? How do we know? How do we determine our system? What do we study here? We study the change in temperature, right? Whose temperature? Air temperature? Resistance wire? No, the base plate temperature. So we are studying the temperature change of the base plate. So the base plate is our system, right? So the base plate is our system, and let's write down the energy balance equation. Then resistance wire or air, etc., they are all the surroundings. So what is the energy balance equation? Q in plus W in minus Q out minus W out is mass times U2 minus U1 plus moving boundary work. This is the general energy balance equation for a closed system. By the way, is it a closed system or an open system? It's a closed system. Why is that? Because the base plate is inside the piston cylinder device? No, the definition of a closed system is when the system's mass does not change during a process. The mass of the base plate is not going to change, so it's a closed system. Then what is the moving boundary work? Is there a moving boundary? Technically, yes. There's a thermal expansion if you have the aluminum, but it is pretty small. So in engineering, we neglect that, right? So practically, we can assume that it's a constant volume, so there's no moving boundary work. But in reality, there's a small change in the volume, right? No? What it is? Now, what it is? So this one, right? I'm not majoring painting, so please excuse, okay? That's the best I can do. So, have you been inside the train? Yeah, while it is, the moving, what makes, when you are in a vehicle, how do you know? If you don't open your eyes, how do you know you are in a train rather than a bus? Right. Every, the couple of seconds, the crane clicks something, right? So why is that? Because the railroads are discontinued, right? So every time, that you have these things, right? So whenever, this weird, the passes through, you feel that, the vibration, right? So why they make like that? Because of thermal expansion. When temperature goes up, this one is going to, get, become longer. So if you, don't cut in the middle, what's going to happen is that the railroad is going to be bent, right? No? That's a thermal expansion. So technically, there is this one, but it's very small. So in thermodynamics, we can neglect that, right? I don't know why I said that, but you can see, there's a thermal expansion, right? By the way, when you go to, the convection heat transfer, especially free convection, you will see the thermal expansion coefficient that we use to determine the amount of heat transfer, the rate of heat transfer when there is, the fluid flow due to gravity. I don't know why I said that, but we will study that later. By the way, what is the fluid flow due to gravity? Oh, yeah. So, yeah, right. So it's a free flow due to what is the force that makes this, the fluid flow due to gravity, buoyancy force. You know what is buoyancy force? Yeah. So, for example, where is the vent in this classroom? Right there, right? But when you go to your house, if you live in Michigan, where you find a vent, the ceiling? No, on the ground, on the floor, right? Have you been, have you lived in Texas? I lived in Texas 10 years, and I never seen a vent on the floor. All the benches, in every single house there, the vents are on the ceiling. Then why vents are on the floor in Michigan? Why vents are on the ceiling in Texas? Right. In Michigan, we want to try to heat. In Texas, they don't want to try, they don't want to heat, right? I still remember when I was the PhD study in Texas A&M University. During the Christmas week, the buses are running air conditioning system. That was my first impression. What's wrong with it? Running a air conditioning system during the Christmas week. Anyway, so the problem is that when you heat a room, if you install your vent on the ceiling, hot air comes in, and hot air is near the ceiling, and the cold air is near the floor. So if you compare the density values between hot air and cold air, which one is greater than the other? When temperature goes up, volume goes up, right? So the density of air goes down when temperature goes up. So hot air is lighter than cold air. So if you install a vent in Michigan trying to heat the house, the hot air is going to be, only near the ceiling. It never comes down. So is that right? No. But if you install your vent on the floor, hot air comes from the floor. So it is lighter than the air in the room. So it's trying to move up. So it will naturally, create airflow in the room, right? That is free flow. But in Texas, they want to cool to cool the room. So if they install vent on the floor, cold air comes in from the floor. They sit there because cold airs are heavier than the air already in the room. So there's no circulation. Only your feet are cold, and you are breathing the hot air. So if they install vent on the ceiling, the cold air comes from the ceiling, so there will be a natural the air flow, right? Air circulation. That's the free flow that you will study later. But I don't know why I said that, but all comes back to this moving boundary work. So that is, when we study this free flow, we use a thermal expansion coefficient, and then we will learn the materials will thermally expand and the compress due to temperature change. I guess I went too far, right? So let's come back to thermodynamics. So there's no moving down boundary work because we can assume that a solid is incompressible. Incompressible means that the volume is not going to change. And the base plate is going to receive heat from the resistance wire about how much? What is the rate of, what is the heat transfer? What is the amount of heat transfer from the resistance wire? The resistance wire has a rating, the 1000 watts. That means the resistance wire is going to create 1000 joule per second. So every second it's going to create 1000 joule. So how much heat transfer from the resistance wire? 1000 joule every second. But that is not the amount of heat transfer. That is not heat transfer. That is the rate of heat transfer. So how do you get the amount of heat transfer? You need to multiply by how long did you use the ion. So what is that? Time. You need to multiply by time. How long? Then there is no energy transfer by work. And what about heat loss? Only 90% of the heat generated in the resistant wire is transferred to the plate. So out of this, 10% is going to be lost. So what is the 10% of this one? From 1000, the 10% is going to be 100. So minus 100 joule per second times T is going to be mass times U2 minus U1. How do you determine U2 minus U1? Specific heat CV times T2 minus T1. So we can combine these two, say 900 joule per second times T is going to be mass times specific heat T2 minus T1. So, oh, by the way, you can see if it is U2 minus U1, we learned that we have to use specific heat CV. If it is H2 minus H1, we have to use CP. However, there is no difference between CP and CV when you have a solid. Why is that? U2 minus U1 is CV, T2 minus T1. H2 minus H1 is CP, T2 minus T1. What makes H? What is the definition of H? H is U plus PV. So this one is U2 plus P2V2 minus U1 plus P1V1 is CP, T2 minus T1. By the way, when you have a solid or liquid, what makes solids and liquids different from gases? They are incompressible, right? So if they are incompressible, these two things go away. So U2 minus U1 is CP T2 minus T1. Oh wait, this one looks the same as this one. So there's no difference between CP and CV. They are the same when you have a solid or liquid. Okay? So then, if you look at this one, you see CP. So this can be, there's no difference between CP, CV, or CP as long as you have a solid. However, if you go to the field, the people like to say CP more often than CV, even though there is no difference. So many people you will see, that they call CP for specific heat of solid or liquid. Okay. So don't get confused when you see this change between CV and CP, okay? Then from this equation, we have T2, the final temperature, 200. What is the initial temperature? 22 degrees Celsius. What is the specific heat? Right here, 874 joule per kilogram Kelvin. And we have everything. Time is the unknown. And what about the mass? Oh, we don't have the mass. How do we determine the mass of this base plate? The mass can be determined by density times volume. What is the density? 2,770 kilogram per cubic meters. How do you determine its volume? We know the surface area and the thickness. So the surface area is 0.03 square meter times the thickness, 0.5 centimeters. 100 centimeters is 1 meter. So it's going to be 0.005 meter. That is the volume. Okay, so this thing goes in here. So we have everything. Can you determine the time? Yes, we can. Time t. Okay. Any question about this problem? What's the final answer? I don't know. I don't trust the solution from the book. You don't trust the solution from the book, okay? This is the last problem for a closed system, then we are going to talk about an open system. An electronic device dissipating 25 watts has a mass of 20 grams and a specific heat of 850 joule per kilogram degrees Celsius. The device is lightly used and it is on for 5 minutes and then turned off for several hours. So the initial temperature of our system, which is the device, is going to be 25 degrees Celsius. And we want to determine what is the final temperature after using it for 5 minutes. Okay? And the amount of heat transfer to the system is going to be 25 watt. But watt is not joule times the time of the duration. So let's solve this problem together. An electronic device dissipating 25 watts, and this device is our system, and it's a solid, so it's a closed system. So the energy balance equation for closed system is going to be this one: Q in, W in minus Q out minus W out is going to be mass times U2 minus U1 plus moving boundary work. And we know it's a solid, so there's no moving boundary work. And the amount of heat transfer is going to be 25 watts. 25 watts times time T. And there's nothing else. It's going to be mass times U2 minus U1. Can be Cp times T2 minus T1. The mass of the system is going to be 20 grams. 1,000 grams is 1 kilogram, so it's going to be 0.02 kilograms. Specific heat is known, 850 joule per kilogram degrees Celsius. The initial temperature is 25 degrees Celsius and 25 watt times T, 5 minutes. So 5 minutes is 1 minute is 60 seconds, 300 seconds. So we have everything. Can you determine the final temperature? Yes, we can. Do I have it? 466. But I don't trust this value, so you do your own calculation, okay? So if you use this electronic device for only 5 minutes, if you use this cell phone only 5 minutes, the temperature becomes 466 degrees Celsius. So they need to hire new mechanical engineer, right? Who studied thermodynamics. So can this electronic device survive at this temperature? No. So what can we do? One way is going to be add a heat sink. So heat sink is nothing sophisticated. It's just a mass that can share the amount of heat transfer. So I'm going to add 500 grams of aluminum on top of this electronic device. So some of the heat goes into this electronic device and heat this aluminum block instead. So we can lower the final temperature. Okay? So let's do that. Then let's write down the energy balance equation. Now, what is our system? After adding this aluminum block, your system is going to be two. The electronic device and this aluminum block. The temperature of this electronic device and aluminum block are going to be the same. Okay. So let's write down the energy balance equation again. Q in plus W in minus Q out minus W out is going to be mass of the electronic device. Let's say ME and UE2 minus UE1 plus aluminum MAR and UAR2 minus UAR1 plus WB. So it's a moving. They are both solids, so there's no moving boundary work. And neglect these three, and the amount of heat transfer is going to be 20 watt, 25 watt times T is going to be mass of this electronic device. By the way, you can calculate this one by CP, T2 minus T1. So we have the electronic device mass times CP, T2 minus T1. This one is for the electronic device plus mass times specific heat, T2 minus T1. This one is for the aluminum. And the mass of this electronic device 0.02 kilograms. Specific heat is 850 joule per kilogram degree Celsius. T1 is 25 degrees Celsius. Mass of the aluminum block is 0.5 kilograms. Specific heat of aluminum block is 0.903 kilojoule per kilogram degree Celsius. So be careful. There's a joule, there's a kilojoule, okay? And T2 minus T1, T1 is 25 degrees Celsius. So the only unknown is T2. So from here, you can determine T2 approximately 41 degrees Celsius according to the solution, but you do your own calculation. Because I don't trust this value. Okay? So just by adding heat sink, you can decrease the temperature rise by this much from 466 to 41. That's what heat sink does. Any question? Where do we use this heat sink in our real life? So let's say that for today's dinner, I'm going to cook some noodle, and then I put my the saucepan on the stove, and then turn it on, and there were the water and pasta and etc. I completely forgot because I went in my room and then playing a video game. I completely forgot about that. Later I saw that there are the lots of the fire comes in. So what I do, just grab and then throw it away. In the sink, you can do that, but it's going to burn your fingers, right? So what's the best way in that case? You wash your hands first. So you make your hands wet, then grab it. So it's gonna be not as hot as the without water. No? No. Okay, that was too much, right? So have you been to a circus? The people trying to play with fire. So sometimes you see a guy trying to put his hands in the middle of fire. But what he does is that he usually pour his hands into he wet his the hands in oil. Have you seen that? Oh, yeah. So what makes the he doesn't get burnt in the fire is that the fire needs to heat the oil first before the transferring heat into your skin. So the temperature of the temperature rise of your skin is limited because you have a heat sink, which is oil. No? So sometimes in the kitchen when you cook something, if you think that it may be hot, like oh right, when you cook when you cook egg, when you make a boiled egg, how you do that? You boil it, right? And how are you going to grab it out? You can use a spoon. Okay, let's assume that there's no spoon. Then you need to wet your hands and then grab it and then put it outside. Then you don't get burned. What about if you want to open the shell? How you do that? Just do it. You will get burned because it's hot. Then the best way to do it you wet your hands and then try to crack it. Then you get unlikely, or you can use an ice, or so one way is that you wet your hands, so you are actually adding a heat sink into your hands. Okay, that's not a good example. Huh? If you don't have it, but usually when I prepare boiled eggs, I use water. So
put them in like an ice bowl beforehand, perhaps. You're supposed to put, like, how they tell you to do it, you put them in like a bowl of cold water.
I'm not that patient. So usually when you need to touch something that is hot and you don't have any other tool, you need to use your bare hand. The best the scenario is going to be wet your hands, and at least it limits the temperature rise of your skin. Okay, what time is it? 7 minutes more. So that's everything about chapter 3, a closed system. So what we learned is how to evaluate a property by using a steam table. That's what we did first, right? And then, we studied the ideal gas equation and specific heat, to analyze a pure system such as pure gas, solid, or liquid. And then, eventually we use this energy balance equation to analyze, a closed system thermodynamically. So in chapter 4, what we are going to do is that we are going to use the energy balance equation for an open system, okay? So before going, going to solve any problems in this open system, we need to review, what kind of energy balance equations did we use for an open system. So open system means there is a mass change, and to have a mass change, you need to have either inlet or exit, right? So this is a typical diagram for an open system. We have inlet, which is number 1, exit, which is number 2, and there can be either heat transfer Q or energy transfer by work W. However, when we study open system, the most open systems that we study as an engineer are studies flow system. That means time independent. If you use a time independent system, it is convenient to use rate form, okay? So instead of QWE, we use Q dot W dot E dot, etc. So technically, energy balance equation or unit time. So what is the general energy balance equation for a steady state open system? We have Q in plus W in. These are heat transfer and energy transfer by work, but we prefer using rate form. So divide Q by T, it's going to be Q dot. Divide W by time T, that's W dot. So when you see that on top of a letter, that means that this letter divided by time, okay? And we have energy transfer the rate of energy transfer by the mass goes in. So there's a M1 goes in. There's a M2 comes out. And if you use a rate form, it's going to be M dot mass flow rate. So M dot number 1 has enthalpy H1, kinetic energy V1 square over 2, plus potential energy, gravity, elevation Z1. Okay. So these are energy transfer to this control volume open system. And energy transfer out of the system, we need to consider the rate of energy transfer by heat comes out, the rate of energy transfer by work comes out, the rate of energy transfer by the mass. So Q first, Q dot out, W. W dot out and not the mass plus M dot at the exit number 2, flow rate. This one has enthalpy, kinetic energy, and potential energy. So this is the general energy balance equation. So we are going to use this energy balance equation to solve any open systems thermodynamically. So there were many different devices that we studied in EGR456. And here in review, we are going to study 2 systems. One is a mixing chamber, and the other one is heat exchanger. Okay. So mixing chamber first. A mixing chamber has 2 inlets, hot water and cold water, and mixed and warm water comes out. So how can we study this mixing chamber thermodynamically? So basically, we have 2 inlets. So in this case, we had only 1 inlet. So now I'm going to create another inlet, which is number 2. Then exit is going to be number 3. Then the energy balance equation, we have extra additional inlet. So M dot number 2, H2 plus V2 square over 2 plus gravity elevation Z2 is going to be the same as this one. And here we have exit number 3. So this is the energy balance equation for a mixing chamber. What about mass balance? The sum of M dot number 1 and M dot number 2 should be the same as M dot number 3, the conservation of mass principle. Okay? So the mass balance equation is M dot number 1 plus M dot number 2 is going to be M dot number 3. That's all. Let's solve a practice problem together. We have a hot water stream at 80 degrees Celsius enters a mixing chamber with a mass flow rate of 0.5 kilograms per hour. No, per second, where it is mixed with a stream of cold water at 20 degrees Celsius. If it is desired that the mixture leaves the chamber at 42 degrees Celsius, determine the mass flow rate of the cold water stream. So when you touch this water, do you feel it is hot or cold? It's hot because the temperature is greater than your body temperature. What about if the temperature is 32 degrees Celsius? Do you feel that it is hot or the cold or warm? No, you feel that it's cold because the temperature is less than your body temperature. So it changes the heat transfer direction, right? Due to the second law of thermodynamics. So let's study that. We have this energy balance equation. First of all, you can assume that there is no kinetic energy change or potential energy change. So you can neglect 145. So we can stop here and continue this problem this Thursday. Okay. Any question? Any question? Oh, today, we studied very interesting, the trains and venting systems. I don't know why I said that, but it was fun to discuss, right?